All right, so this is a little extra video which is going to cover how to parameterize things. This is definitely a review because this is all Calculus 3 material, but it's so important for what we're going to be doing with vectors and line integrals that I'm just going to kind of do a very, very quick reminder of how to parameterize things. And we're just going to do, I think, the 2D cases because it extends into 3D very naturally. And if you'd like, you can go back into, I believe, chapter 13 in the textbook, and it talks about it. But the idea is you know, if we have a line, okay, going between 2 points, right? So this is the process, how to parameterize a line. And maybe first and foremost, why might we even care about parameterizing a line, okay? To parameterize a line means to take an equation like y equals negative 2x plus 4, and to write this, instead of it being an equation of two variables, it's to write both of the variables in terms of one variable. The simplest way to parameterize something is literally something as simple as saying let x be equal to some random variable t. And if we do that, then y will be a function of t. It'll be negative 2t plus 4. And why might we care about this? Well, you know, maybe this little equation that I wrote right here represents the amount of money our company makes. And it's money that's based on x. And if x is like the number of toys that we make, you know, that's cool. But maybe the number of toys that we make is based on what day it is. And so in this case, what we've done is we've said, oh, so the number of toys that we make is based on this equation right here, what day it is, t. And that means that the amount of money we make could be thought of, instead of it being in terms of x, we could think about it also in terms of the number of days or what day it is. Right? And so that is some useful information. We basically get kind of 2 bits of information for the price of 1. And it turns out, hopefully we remember from calculus, that when it comes to doing derivatives and integrals, having only one variable to take derivatives and integrals of tends to be much more convenient than having equations where there's 2, 3, 4, or 5 variables in it. So one thing that we cover in calculus 3 is if you're given the equation of a line that's going through 2 points, okay? And again, I'm going to do this in the 2D case, but it extends very naturally to the 3D case. So let's pretend this is the point 1, 4, and let's pretend this is the point 7, 2, okay? And the question is, how do we come up with some vector equations, right? Some vector function r of t that tells me, you know, exactly where I'm going to be on this line at any given point. So remember how this works, like how a vector function works, how this parameterization works, is that we are going to describe x in terms of some variable t, and we're going to describe y in terms of some variable t. And what this does is this vector function r of t will points vectors at every single point that is on this line at some given time t. So maybe at t equals 0, we're here. At t equals 1, we're here. Maybe at t equals 7, we're here. T is equal to 28, we're over here. It doesn't matter, you know, how long it goes, how long it takes. The idea is that we will sketch out this entire line. Now, why do I have these t values so spaced out? Because the point is depending on what your parameterization is, will tell you where you're going to be on this line. So if we very quickly return to my little example over here of toys, and toys based, or the money that we make, which is y, and x is the number of toys we sell, and t is the number of days that we've maybe been running our company. If I modify, right, actually here, before I modify this, on day, let's say t equals 2, right? How many toys am I making? Well, I'm going to be making 2 toys. How much money am I going to be making? $0. I'm breaking even. Okay, cool. But what if I change my parameterization, right? What if I change my parameterization to be t plus 7? Okay. which in turn is going to make my y parameterization negative 2 times t plus 7, which is negative 2t minus 14. Okay, so now how much money am I making on day 2? Well, on day 2, I'm making 9 toys, but maybe making 9 toys has caused me, some financial woes, and you can kind of see that we're going to get y is equal to negative 18. So based on this completely different parameterization, it still is parameterizing the same line, but because of how I parameterized it, it has changed, that on day 2, now I'm making 9 toys, and now I'm losing $18. And so the point is that parameterization allows us to kind of incorporate, for the same values, right? For the same x values and for the same y values, I can assign to them different points in time that they happen. And you can think about it like going on a road trip from here to New York City. If one person could be driving 100 miles an hour, they are going to be, at different points versus me who drives really slow, right? Maybe I'm only here at t equals 3, but maybe the other person is here at t equals 3, and we would both be traveling the same path, right? We're both traveling the same exact line, but because of how we decide to parameterize our motion in terms of time tells us that we're going to be in a different location based on a different time. So the point of parameterization is to incorporate time in some meaningful fashion. And so that's what we're doing here. And so from Calculus 3, the easiest way to do this was if we were given a line that goes between 2 points, we said, okay, well, this line has to start going through one of these points. So I'm going to say, okay, let's say that when t is equal to 0, we are going to we want the vector 1, 4. Okay, that's where we want to start. And then we say, okay, we know at some point, right? At some point, we need to be having the vector 7, 2, right? We need a vector that points to the point 7, 2. And so the idea is that we kind of construct r of t, right? We construct this vector equation by saying, okay, look, we want to start at the vector 1, 4, and then after some time, we want to end up at the vector 7, 2. Okay, so how do we do that? Well, courtesy of vector addition and subtraction and stuff like that, what we really need to find is we need to figure out what vector kind of points in the direction of 7, 2. Okay, because remember, we're starting aiming at the point 1, 4. And the way vector addition works is if I take that red vector and I add it to this yellow vector, it's going to give us the green vector. And so how do you come up with the yellow vector? Well, it's very simple. You're going to do the final point minus the initial, and you're going to get, in this case, this yellow vector is the vector 6, negative 2. Okay? And so what that says is if I take the red vector, right? So if I take the red vector, maybe I should have this be red, 1, 4, and I add the yellow vector, 6, negative 2, I'm going to end up at this point, right? But what if I only wanted to end up halfway, right? What if I only wanted to end up here? Well, then I would take the red vector, but I would add only half of the yellow vector, right? I'd add half the yellow vector, and it would take me to whatever point is halfway between 1, 4 and 7, 2. And we could do this for any point. What if I want to end up there? Oh, then I would add 3/4. Okay, what if I wanted to end up over here? Oh, then I would add, twice the yellow vector, right? Because if I take that, wrong thing. If I take that yellow vector and I extend it twice as long, I'm going to end up at whatever point is right here. And so the way that we generalize this is instead of, playing a guessing game, we just put a t here and we say t can be any real number, okay? Or in other words, t can be from negative infinity to infinity, any real number that we want. And that basically allows us to kind of move this red vector and cover every single point that is on this line, okay? Now, we've done parameterization before, right? So maybe if we consider the equation x squared plus y squared equals 1, which we know to be the unit circle. Okay, so let's put on the unit circle here. Okay, now I could parameterize this in some way. For instance, if I say let's let x be equal to t, okay, if I just choose x is equal to t, what does this do? Well, first off, I'm going to rearrange this equation to be y is equal to plus or minus the square root of 1 minus x squared by just moving some things around and taking a square root. And so what does this do? If I let x be equal t, then y is going to equal plus or minus the square root of 1 minus t squared. And, you know, technically this is a parameterization for this circle, right? This works. I could have picked x is equal to t plus 6, and then y would equal plus or minus the square root of 1 minus quantity t plus 6 squared. And this would be another parameterization that would describe this circle. However, the timing of this second one would be different from the timing in the first one, right? Maybe at t equals 1, I'd be here with the first one, and maybe at t equals 1, I'd be here for the second one. Okay, so that's the only thing that changes, but the path is still the same. And we saw that even though we could do these parameterizations, that maybe they weren't the best parameterizations. And so we introduced, for instance, for a circle of radius 1, that if x was equal to cosine of t and y was equal to sine of t, right? We use t instead of theta because we're adults now. That if we do this and say t can be, you know, again, any real number, that is a nice parameterization where you give me t, and we know, for instance, that when t is equal to pi over 2, we end up here, and when t is equal to pi, we end up over there, and, you know, so on and so forth. Okay, and I want to comment, I did make a slight mistake earlier where I said that t could be any real number with this parameterization. That clearly doesn't work because based on the parameterization up at the top there, we can kind of see that if t is larger than 1 or t is less than 1, this doesn't really make any sense. And this should actually kind of ring a bell because on the unit circle, does it make sense for x to have a larger t value than 1 or a smaller t value than negative 1? Of course it doesn't. But if we parameterize it this way, t could be anything, right? Because, you know, no matter what t value I pick, I just keep going around and around and around and around and around the circle, whether I'm going this way or maybe I go the other way if t is negative and so on and so forth. So this parameterization has a really nice kind of property about it. So this is just a very, very quick video that's kind of scuttling through this. I would recommend that if you don't remember how to do these things, you revisit chapter 13 and practice, because we are going to use them profusely starting immediately in the next video. So just kind of make sure you have this under your belt, especially the one for line segments. It translates the same if I had like the parabola y equals x squared. I could create a parameterization, and of course the simplest one is to just let x be equal to t, and then y is equal to, what would y of t be equal to? Well, y of t would be equal to t squared, and this would be a parametric representation of a parabola. And there's pros and cons to picking certain parameterizations, and it'll be kind of up to us to figure out which ones we're going to use. But that's going to do it for this video. Head on over to the next one where we finally start talking about line integrals.